Imagine looking at a temperature map of the Earth, mapping out the last century or so. Just about every landmass, every ocean basin is painted in these angry, vivid shades of crimson and dark orange.
Right, the classic heat map we're all used to seeing by now.
Exactly. We all know the story. The globe is heating up rapidly. But right in the middle of the North Atlantic, just southeast of Greenland, there's this stubborn, glaring blue patch doing the exact opposite.
Yeah, it's actually cooled by up to 1 degree Celsius over the last 150 years.
Which is a massive planetary paradox. I mean, welcome to Science Tandy. This is a special edition from Claire and Orescio, designed to look past the headlines and really untangle the actual science for you.
Because there is always more to the story than just the headline.
Always. And our mission today is to investigate this cold blob, or the warming hole, as some scientists call it, in the North Atlantic.
It's a fascinating anomaly.
It really is. We want to figure out if this is a symptom of a catastrophic failure in Earth's ocean currents or, just the noisy atmospheric trick. Because to me, this looks like a flashing warning light on the planet's dashboard.
Well, I'd say we need to exercise a bit of scientific caution there. I mean, oceans are incredibly noisy systems.
Fair enough. But we definitely need to figure out what's causing it. So let's establish exactly what and where this thing is.
Geographically, we're talking about a specific region of the subpolar North Atlantic,
Hmm.
basically right between Greenland and Iceland.
Right. And the timeline is important here, too. It's been progressively cooling about a century and a half.
Exactly, which of course makes it stand out against literally everywhere else on the planet.
And before we get into the mechanics of why, we have to address this very persistent myth that pops up practically every time this anomaly makes the news.
The climate skeptic argument.
Yeah, you'll hear people say, look at this cold patch. How can global warming be real if this massive part of the ocean is literally freezing?
Right, which completely misunderstands the physics of this system. Local cooling does not disprove global warming.
Right. It's not a gotcha moment.
Not at all. It's actually a symptom of global warming messing with how heat is distributed. The Earth as a whole is gaining heat, but the mechanisms shuffling that heat around are, well, they're struggling.
Okay, let's unpack this. Think of it like a faulty radiator in a house with a totally broken thermostat.
That's a good way to look at it.
Yeah, so the whole house is getting hotter and hotter, right? But one specific room is freezing cold. It's not because the heat turned off globally, it's because the plumbing moving the heat into that specific room has broken down.
And in the ocean, that plumbing is the Atlantic Meridional Overturning Circulation, or the AMOC.
The AMOC.
Right? It's this massive ocean machine. And the core tension in the scientific literature right now is whether this cold blob is the physical fingerprint of an AMOC slowdown.
Because if the AMOC slows down, it delivers less heat.
Exactly. The cooling could just be the result of a stalled heat conveyor belt.
Okay, so to understand why the plumbing might be breaking, we need to know how this massive ocean machine actually works under normal conditions.
Right. Normally you have warm, salty water flowing north from the tropics.
Sweeping up past the U.S. East Coast.
Right. And when it reaches the cold North Atlantic, it loses its heat to the atmosphere.
And losing that heat changes the water itself.
Completely. As it loses heat, it gets colder, obviously. And cold water is denser than warm water.
Makes sense.
But it's also incredibly salty because it came from the tropics where evaporation is really high. And salty water is denser than fresh water.
So it's cold and salty. It's basically as dense as ocean water can get.
Exactly. So it becomes so heavy that it literally sinks thousands of meters down to the ocean floor.
Wow.
And then it flows all the way back south along the bottom. That sinking motion is what drives the whole conveyor belt.
Right, so the disruption here, the wrench in the gears, is all about melting ice.
Yes, specifically from Greenland.
Right, because global warming is melting the Greenland ice sheet. And that pours massive, massive amounts of fresh water directly into the North Atlantic.
Which totally messes with the salinity.
Exactly. It lowers the salinity and the density of the ocean surface. It's like watering down a really dense soup. If the water is too fresh and too warm, it just sits at the top. It can't sink.
And if it doesn't sink, it effectively jams the entire global conveyor belt.
What's fascinating here is how this triggers the salt advection feedback.
Wait, what is it? Salt advection?
Yeah, it's a feedback loop. Basically, an overload of fresh water slows the current down because it can't sink.
Okay.
And because the current is slower, it brings less of that really salty water up from the tropics.
Oh, I see. So less salt arrives in the north.
Exactly. which creates a loop that dilutes the North Atlantic even further, making it even harder for the water to sink.
That is a terrifying loop. So that's the oceanic argument. The AMOC is slowing down, so the heat never arrives. But there's a whole other side to this scientific dispute, right? Yeah, there is. The debate is basically, is the AMOC really to blame? Or is the atmosphere just playing tricks on the water's surface?
Right, the oceanic deficit versus atmospheric tricks. Let's look at the oceanic argument first, because recent studies, like the ones led by Stefan Rahmstorf, are super compelling.
They've done some incredibly detailed work, yeah.
They showed that the cooling in the cold blob extends roughly 1,000 meters deep. It's not just a surface thing.
Right, it's a massive volume of cold water.
And furthermore, their data shows that surface heat loss has actually decreased since 1955.
Which is a very important detail.
Here's where it gets really interesting. If heat loss at the surface has decreased, it means the atmosphere isn't aggressively stripping the heat away from the water.
Right, the wind isn't just blowing it off.
Exactly. The ocean simply isn't delivering it. The delivery truck never arrived.
It's a very strong argument.
Yeah.
But, we really have to look at the rival research, too, because atmospheric shifts are powerful.
Okay, what's the atmospheric argument?
Well, there was a major study in 2022 led by Cheng-Fei He. They used the Community Earth System model, specifically running what's called a slab ocean simulation.
Wait, a slab ocean? What does that even mean?
It's a modeling technique. They basically flatten the ocean into a static 50-meter-deep layer of water, a slab.
With no currents at all, just a stagnant puddle.
Exactly. No horizontal flow, no AMOC. It just exchanges heat with the air above it.
Yeah.
And when they ran historical climate data through this model,
Let me guess, the cold blob still showed up.
it still showed up.
Wow, even without the ocean currents. So how does the atmosphere freeze that patch of water all by itself?
Mainly through shifting jet streams and stronger westerlies.
The winds.
Right, stronger winds act like a fan, increasing wind-driven evaporation, which physically draws heat out of the surface.
Ah, okay. Evaporative cooling.
Exactly. Plus, these shifting winds change cloud dynamics. You get more low-level clouds gathering over the North Atlantic, and they act like a massive shade.
Blocking the sun.
Yeah, blocking solar radiation from warming the water. So between the evaporation and the cloud shading, atmospheric shifts alone might account for, like, 50% of the cooling.
50% is huge.
And there are even alternative oceanic theories, too. Like, maybe the Norwegian current is just strengthening and redirecting the heat away from that area rather than the whole AMOC shutting down.
So it's incredibly complicated. Real quick, just a quick reminder for you listening that along with Science Candy, Claire Noracio also offers Brain Candy, Debate Candy, daily news briefings, classic companions, and classic audiobooks to keep your mind sharp.
Always good to check those out.
Absolutely. Okay, so getting back to it, we've got this massive clash of theories. Rahmstorf says the heat is missing deep down, the AMOC is broken.
Right.
And then Cheng-Fei's model says, no, the wind and clouds are doing it. Why don't scientists just look at the actual ocean data to solve this? Just measure the current.
I mean, they do, but the data is just stubbornly inconclusive.
How so?
Well, to directly measure the AMOC, we use these moored sensor arrays, like the rapid array.
The rapid array.
Yeah, it's a line of sensors anchored to the seafloor stretching right across the Atlantic, but it was only installed in 2004.
Oh, so we only have, what, about 22 years of continuous direct observations?
Exactly, just 22 years. And we measure this flow in a unit called Sverdrups, or CV.
What exactly is a Sverdrup?
One Sverdrup equals 1 million cubic meters of water moving per second.
That is an unfathomable amount of water.
It is. And in the early days of the rapid array, the average strength of the AMOC was around 18 to 19 Sverdrups.
Okay.
But more recently, it's dropped to an average of 15 to 17 Sverdrups.
Wait, really? A drop from 18 down to 15 Sverdrups? That's millions of cubic meters of water per second that just stopped moving.
It's a significant drop, yeah.
Why isn't that the smoking gun? Why can't we definitively declare the system is collapsing right now based on that drop?
Because 22 years is a mere blink in geological time. The ocean has massive interannual and decadal variability. It's a really noisy system.
So a drop might just be a temporary dip?
Exactly. In the scientific literature, you'll see researchers say a localized anomaly is consistent with AMC weakening.
Right.
But that is vastly different from having absolute proof of a long-term collapse. The baseline is just too short.
It's so frustrating that we're trying to diagnose a 150-year-old problem with 22 years of data.
It is.
Yeah.
But that's the reality of observational oceanography.
Okay, but we have to look at the stakes here. What happens to our world, to the listener's world, if the Amos Sea truly collapses? Let's say it drops to that weak state scientists model, like 3 to 6
Or
Sverdrups.
if the subpolar gyre shuts down entirely.
Right. The impacts would be wild. We're talking about rapid cooling in Europe, extreme winter storms.
Significant sea level rise along the coastlines.
Yeah, and the disruption of monsoon rainfall. That's essential for agriculture in Africa and Asia. We are talking about a disrupted planetary life support system.
The agricultural impacts alone would be staggering.
And some models show these tipping mechanisms triggering as early as the 2040s or, maybe after 2100.
Right. And if we connect this to the bigger picture, we really have to pull back from the cable news panic.
What do you mean?
Well, we need to clarify what a collapse actually means in climate physics. It doesn't mean a sudden day after tomorrow instant ice age.
Right, New York isn't freezing over in a week.
Exactly. If a shutdown triggers, it could take 50 to 100 years to fully stabilize into a new weak state.
Okay, so it's a slow motion collapse.
Yes, tipping points are scientifically serious, incredibly serious, but they are very easy to oversell to the public in terms of timeline.
That makes sense. So what does this all mean?
It means we're in uncharted territory.
Yeah. We have this cold blob, and it's a blaring warning light. Whether it's driven primarily by wind or by a stalling ocean conveyor belt, it proves that climate change doesn't just warm the globe evenly.
Right, it's not a uniform blanket of heat.
Exactly. It shatters the systems that keep our weather stable.
And there's one final lingering concept from the research that I think people really need to mull over.
What's that?
Well, if the AMOC slows down and stops transporting heat to the North Atlantic, all that tropical heat doesn't just vanish.
Oh, wow. Where does it go?
It gets trapped. It actively builds up, radically warming the southern hemisphere and the waters right off the U.S. East Coast. The heat has to go somewhere.
Wait, so while the North Atlantic gets this cold blob, the rest of the ocean is just superheating?
Essentially, yes. It's a massive redistribution of energy with huge consequences for sea levels and storms in those trapping zones.
That is terrifying to think about. The machine is broken and the heat is just piling up in the wrong places.
Exactly.
Well, that's definitely something to think about. For more science candy, brain candy, debate candy, news briefings, and classic audiobooks, visit clarinhoratio.com.